we have Professor Dante Kennis with us. He's from IWTH Aachen University, and he's also a group leader at Max Planck Institute for the Structure and Dynamics of Matter. Without further ado, you can start your talk.
All right, well, thanks for the introduction. And thanks to all of you for returning for the last session of the day. And of course, also thanks to the organizers for giving me the opportunity to present some of our research here. So this is research that we did in the last couple of years, and it's cumulated into some type of perspective that we were asked to write. So I took this as a title. We'll understand what that means later on, but roughly we're asking, what can I do with Moiré to emulate certain systems that are prototypical to condensed matter research? So let's jump right in. But before we get there, let me just orient you really quickly about the research that we are doing in general in the group. It aligns all in the pathway of controlling quantum materials or engineering quantum materials. But we do different things along these three pillars that you see. In the first pillar is to use non-equilibrium external stimuli to control quantum material properties. So that is prototypically, let's say, blasting a system with a strong laser, and then the electromagnetic forces onto the system can effectively alter the properties that the crystal exhibits. One prominent example is that you have a periodically modulated field when the laser is on, so you're shaking your system periodically, and then you can show that that effectively alters the Hamiltonian that the system feels, and that of course will lead to different material properties. And that goes under the name of Floquet engineering and has become quite famous in the field. But there's other things, like you can now surgically address certain phonon modes. So you can take your laser to precisely kick one phonon mode, for example, which would be another way of inducing non-equilibrium or controlling your material with non-equilibrium means. Now the second pillar that we're into is to use different stacking techniques in the field of 2D materials. So Van der Waals heterostructuring to control material properties, and of course that is the thing that I want to concentrate on today. And then the last pillar is an emerging research field that our group has picked up. It's subsumed here under the name of cavitronics, and that's the idea that you place mirrors nearby to your material, and then you ask questions such as, now that the light field is extremely confined, the quantum properties of light becomes relevant, and can now, for example, even quantum fluctuations play a similar role as the external driving that was induced in this first column. The first and third column I will only mention in a one sentence outlook type of way. But if you want more details on this, there are some recent perspective review types of articles that we were asked to write, and they are given here. So if you're interested in any of that, I invite you to look this up. We'll now jump into the field of Van der Waals materials heterostructuring, and in particular Moiré engineering. And since I don't know, I had a bit of a uncertainty how heterogeneous this crowd would be. I wanted to start very basic. If this is too basic for you, you can doze off for a couple of minutes. I hope we'll get to more interesting topics in a second. But to get everyone on board, the Moiré effect is something that is not quantum. You can see it in the world, in your everyday's world, all the time if you look for it. And I took some examples shamelessly off Wikipedia here. So we have this, fine wall brick houses. For example, the guest house is such an example. If you take a photograph of that, sometimes it will happen that the finite resolution of the camera will interfere with the fine structure of the wall brick and make this nice geometric interference pattern, these fringes here, circular fringes. Of course, this is not how the house was built, yeah? This is an aid effect, a geometric aid effect of that resolution problem. But of course, you can play similar games with any kind of pattern. Yeah? So if you take a pattern and you either slide it, you rotate it, or you have slightly mismatching patterns, you always get a Moiré effect. Another example are concentric circles that are just shifted left or right. This is the next example here. You see this large wavelength pattern emerging as you go to small shifts. But you can really do this with anything. So you can just draw parallel lines, two sets of parallel lines, red and green. This is this example here. And when you now, and this will be an example that will actually be relevant later on in the talk, so I challenge you to keep this in your head. If you rotate this slightly, you will see that there are these one-dimensional, very long wavelength superstructures emerging. It's just geometric interference. If you're too bored right now, you can try to create your own Moiré pattern by taking a picture with your cell phone of your laptop or your tablet. All right. Good. So now we have already seen in Oscar's talk a very nice introduction to this, so I can be very fast here. We can transfer this idea to the field of 2D materials engineering. And, well, the most natural candidate maybe is to look at graphene. So graphene is a honeycomb lattice of carbon atoms. If you take two of these slices now, put them on top of each other, and rotate, you just geometrically induce a similar pattern. It has this plate, I'm not sure. So if you do this, and we have seen this before, you get a large Moiré unit cell, a super pattern, by the effect that we have just described. And in this Moiré unit cell, you have different stacking registries of your carbon atoms. Sometimes your carbon atoms will sit dead center on top of each other. These are called AA regions. And sometimes they will be displaced a bit. Yeah? And that defines, a varying local registry of the carbon atoms. And now you can ask, how does this affect the properties, the physical properties, electronic properties, phononic properties of my crystal? So I have to move forth and back a bit, but it's not too distracting. Okay, good. So what have we gained? By this twist angle degree of freedom, this is a continuous degree of freedom that you can tune through. You now have a control knob to control the periodicity in your system. Yeah. So with this trick, this is a static picture of just two honeycomb lattices superimposed at 10 degrees, so rather large angle, and you can nicely see this large Moiré superlattice emerging. And with that, you have controlled your lattice constant, your periodicity in your system, from this small, not native carbon kind of distance scale to this much enlarged lattice constant by just putting the two on top of each other. Yeah? So in general terms, this twisting, this arena of twistronics and Moiré engineering allows you to control the lattice constants, the periodicity of your crystal. So why is this interesting or important? And again, I'm going to use a very naive, simple picture here. A better picture was introduced by Oscar, of course, earlier. But what you do is you kind of control the distance of the lattice sides. Yeah? So you just introduce this new length scale. And what this will do, even if you look at, let's say, not some Dirac cones or something like this, just electron gas kind of dispersion, what that means is if you now backfold many times because you have increased your lattice constant by a huge factor, you get a much smaller Brillouin zone, you backfold the bands over and over again, and you get these very, flat bands down here. And now the additional ingredient that you need is that there's some hybridization that opens the gaps at the end of the Brillouin zone, and then you have very flat bands. Yeah? So this is a very naive cartoon to understand, the basic concepts of this. And now let's see what kind of things we can do with this on a physical side. All right, so I put conventional solids here. That's, of course, semantics. That's, for me now, everything that's not twistronics. Yeah? So it's a very loose sense of using that word. And when you grow a solid, for example, you know that everything is dictated by chemistry. Yeah, your chemistry will just say that your atoms are of roughly the order angstrom apart, and that length scale will define typical kinetic energy scales, bandwidths of electrons. That's how easily your electrons move through your crystal. And those will be roughly in the EV range. Yeah, I'm making broad strokes here. And I will not deny that there has been tremendous advances in controlling these materials. Yeah, so it's not to bash that field, but there's also limitations. So one of the things that, of course, work very beautifully is you can introduce a different filling by putting dopants in. This will also create disorder, and sometimes maybe you don't want this. So here comes the arena of twisted van der Waals materials, where the difference now is that we have this controllable twist angle, that's a continuous degree of freedom, that defines a new length scale. Yeah, that length scale is maybe at 1 degree, or about 1 degree, 100 times larger than the original length scale, so it's now at, let's say, 10 nanometer instead of about angstroms. And that will quench your bandwidth, your kinetic energy scale, with a similar effect as we have seen in the animation, by about a factor 100. So it will quench it from EV to roughly tens of MeV. And that's completely tunable by the twist angle, so that's, of course, a nice control knob that you can use. And so, as a little bonus, because you're doing 2D materials, you can also control the filling by using gates. All right, so in general, why is this interesting? Well, what this means in principle is that you can control the kinetic energy scales. You can make those scales smaller. Yeah? Why should you care about this? Well, usually there's also other scales in your system. One example that we have talked about already in this workshop are potential energy scales, yeah? Electronic interaction scales. Now, if you make the kinetic energy scales smaller, comparably speaking, you promote the relevance of the competing scales, yeah? Like the interaction scales. So you can tune maybe into a regime of stronger coupling between the electrons. But you could also play this exactly same game with other energy scales, spin orbit coupling, you know, magnetic energy scales, you name it. Yeah? All right, good. So that's what we're in for. We want to make kinetic energy scales small, and then we want to look at, you know, outsizing effects of other energy scales. All right, and here I can also be rather quick because we had this in Oscar's talk as well. What really kickstarted this field, I think, was this report of this phase diagram here, where we have temperature on the y-axis and carrier density tuned by a backgate on the x-axis. And you see certain fillings where you have a more resistive state in the middle here, this red region, more resistive, and then it's flanked by these blue regions here, which are labeled superconductor because the resistance plummets down to approximately 0. Yeah? So that got people really, really excited because this phase diagram just has an apparent similarity to this phase diagram up here of the cuprates, which of course has been bothering physicists for a long, long time. Yeah? So you see, we have temperature again on this axis, and we have filling on this axis now, controlled maybe by putting dopants in. And well, you have in the middle here an antiferromagnetic state, it's more resistive, and then flanked by these superconducting domes. I think it's fair to say, and we had this conclusion earlier, that there seems to be an apparent similarity, but how far this analogy will actually reach in the end is, I think, at this stage completely unclear. It got people really excited because the hope was initially that we can maybe understand this in a chemically much simpler compound involving only carbon here. Yeah? So that was one of the big pushes to the field. Where this will turn out to be true in the end is, I think, doubtful. Because we heard, for example, all of these beautiful topology playing a role in this part, making the physics more rich. All right, there's one more signature that often isn't talked about that I want to highlight, and that is that a signature that's also often seen in unconventional superconductors, and that is nematicity. Yeah? So if you think about unconventional superconductors, you will often see that it's tied to some nematic order. And a similar kind of thing happens in twisted bilayer graphene. And this is an STM image. So our experimental colleagues took this image here. If we look at this panel here, yeah, just an STM looking at, the STM basically measures the local density of states, yeah? And you see that there are these white blobs here. And these white blobs are exactly corresponding to the AA regions. You can show that there in your Moiré unit cell, when carbon sits on carbon, the local density of states is extremely large, so you get a lot of signal in the STM. Now, this is at some filling where you would say correlations are probably not so relevant. Now, you tune the filling, and what happens at a filling where you would say, oh, here I'm in the regime where correlations might be more relevant, this nicely rotationally symmetric, threefold symmetric picture here, C3 symmetric picture, develops these elongated stripes. So it's breaking the rotational invariance by tuning the filling, yeah? Pointing toward that's probably something to do with correlations. And we want to now go beyond twisted bilayer graphene, and this will be in line of the spirit of the rest of this talk. And now we want to look at twisted double bilayer graphene. So you take a bilayer of graphene in its natural banal stacking, another bilayer, you put those two on top, and you start to twist. Yeah? Additionally, you apply an electric field perpendicular to the stack, and that will open gaps in the bilayer graphene. We've also seen this in the prior talk, in this nice workshop here. So now you don't have Dirac cones. Yeah, you have a gapped system. But you can play exactly the same games with twistronics and reducing these kinetic energy scales, as we have seen for the twisted bilayer graphene case. It's actually easier because in these gapped systems, this magic angle structure is absent. So you could say, oh, it's not so interesting. Yeah, so this magic angle structure is tantalizing. But for experimentalists, it's also annoying. Yeah? If you have this magic angle structure where the bandwidth rapidly plummets down, little angle variations that you always have will have huge effects on your system. Yeah? So your bandwidth will be disordered rather strongly. Yeah? If you have a nice, smooth, continuous function, then you can maybe live with these angle variations. And because that's easier to control experimentally, one can do this experiment, and these results are shown here. Again, for some filling, you find a nicely C3 symmetric signal. You have these defects, so ignore that for now. And you go to a different filling where you would say, okay, here correlations really play a role, and you see elongated stripes, one-dimensional structures, basically spanning this much, much larger field of view. Yeah? Because this is much more forgiving on twist angle variations, here the field of view can be that large. Here you see it's much, much smaller field of view. This is only a couple of Moiré lattice sites. All right, good. So with this I want to stop the introduction of this talk. I just want to end on a high note. So we took just a classification of phenomena of condensed matter research, and we classified them in terms of electronic topology or electronic relations, or maybe the interplay of the two, giving rise to this phenomena. And I would wager a guess that most of you that do research in condensed matter physics would probably find themselves somewhere in this table. Yeah? And then you see little references attached to these phenomena. This is not an exclusive list, yeah, but there's some references attached to almost all of these phenomena, and the references are exclusively and only in the field of Moiré heterostructuring. Yeah? So Moiré engineering gives rise to all of these beautiful, or at least is proposed to give rise to all of these beautiful effects here. It's really a good time to be in the field of engineering 2D materials. If you want to look up the details, this is published here. But with that, I want to come from the introduction to the main part of the talk. And I brought this figure of this aforementioned perspective article that we wrote, because it can easily serve as an agenda for the rest of the talk. So from now on forward, what we will do together is simply go away from graphene. Yeah? I'm a theorist, so for me that's very easy to say. I don't need to go into some, do things in vacuum or something like this. I just assume that everything that's chemically stable I'm allowed to look at. And we're just asking, can I exploit that expanded catalog to do other things that are interesting? Yeah? And what we'll do together is we'll explore some of these together. In particular, we'll see how we can effectively engineer triangle lattices as low energy theories using Moiré engineering. And we'll see how two-dimensional systems being placed on top of each other can effectively realize one-dimensional physics. Then we're going to switch gears a bit and look at collaborations with experiments, talking about quantum magnetism, and then also, if we have time, Moiré excitons. So that seems like a very, very, very full schedule for the next 2 hours that I will be talking about. But if we don't get through, that's fine. These are separate kind of topics, and I can stop any time. So it's, I think, more important if you have any questions to interrupt me. All right, and then, as I said, in one sentence in the outlook, I will try to connect this to the other pillars that I've been mentioning, driving systems with light, or cavitronics at the very end. All right, so let's just jump right in, and let's do a baby step. Let's take our beloved graphene, which has 2 carbon atoms in the unit cell, and let's replace one atom with boron and one with nitrogen. And then so there we have HBN, which we love, right, for encapsulation reasons, but we could also say, can I play similar games now with this new material? Yeah? Instead of carbon, replace one by boron, one by nitrogen. That's it. And we wanted to see what's similar, what's different. Yeah? And what's similar is that you can still, of course, produce a Moiré pattern, and will still give rise to flat bands. We'll see that in a second. But there's already, at the geometric interference level, there's one big difference, and that is that now there are 2 different inequivalent configurations at small twist angles that give different physical results. Yeah? So there's a small twist angle, like in graphene, but because you now have 2 inequivalent atoms, there's also 60 degrees minus a small twist angle. And you see that those are physically different configurations because they're plotted here and here, and I highlighted for you the regions as red and blue circles respectively, where the nitrogen sits on nitrogen and where the boron sits on boron in this kind of configuration. And you see in this configuration B, these are at the same space in the Moiré unit cell, while here they are distinct spaces. All right, so let's look at this configuration B in a bit more detail here. And now we just take the system, we relax the structure, we push this many thousand atom system at small twist angles through a DFT characterization. So that connects to the very first tutorial that we looked at. And we just use that machinery to classify the electronic band structure of this huge unit cell system. Yeah, it's a brute force calculation, takes weeks. Okay, but can be done. All right, so at small twist angles, so this at 2.64 degrees, we see another difference. There are these flat bands emerging as promised. They split off the valence band here. That's good. You want flat bands that are separated from the rest, right? Because otherwise, there's no point in talking about flat bands. But now there's families of flat bands. Yeah? So if we would go to smaller twist angle, there would be yet another family of flat bands popping up. Yeah? You see there's red, yellow, blue. Yeah? And you can ask, what's the properties of all of these flat bands that are emerging? We stopped at 2.64 for one, because it gets very heavy, computationally heavy to go smaller. And for two, and that's the reason that was mentioned earlier also, at very small twist angle, you get more and more reconstruction, and it doesn't really make sense to talk about these kind of systems. All right. The next difference, and I hinted at that before, boron nitride is a very good insulator, it has a huge band gap. That's why we're using it all the time. So when you look at the behavior of the bandwidth of this red band here, for example, then you will see that at small twist angle, this does get flatter and flatter, but there are no magic angles. Even if I would continue this, there's no magic angle dip structure that we have seen. All right, so that's, again, good for experiments, maybe bad for intellectual richness. All right, so then what we can do, and I didn't bring this plot, but you gotta believe me or look at this paper, you can zoom into this red dispersion relation, and you will see this perfectly follows the dispersion relation of a nearest neighbor hopping triangular lattice. So now we can take this lattice and we can add local interactions. Yeah? So we're neglecting here for simplicity the longer range interactions, which, as we have seen, might be very relevant, but are not part of this study. And then we just ask the question, let's assume we could dope here, which is, of course, experimentally speaking, extremely difficult. Maybe with photodoping, but this is a huge energy difference, right? So it's going to be very hard, but for theorists, it's a number that you put. And we are studying the system with respect to half filling. So mu equals 0 is half filling, and then we can tune this chemical potential. And on the y-axis, we put the ratio of the potential energy scale to the kinetic energy scales. That's the thing that you tune with the twist angle. Yeah? As you make this twist angle smaller, you go to larger interaction space. And then we use a method called functionalization group. I skip all the details about the methods because it's getting complicated. If you have questions about functionalization group, I'm very happy to chat with you. That gives you a phase diagram like this. Yeah, and you see, okay, you can go into a metallic state when interactions are too small to, at these temperatures, stabilize collective order. Then at very large interaction, you, in this method, find that there's some spin density wave order emerging. And at these, intermediate interaction strength, where the spin density wave is not rigid enough to quite form, but you have lots of fluctuations in this order, we actually stabilize an unconventional D-wave superconducting state. Yeah? All right, so that was one thing that we could do. We could go from graphene, carbon-carbon, to taking boron nitride. Okay, now let's make a bigger step away from graphene, and let's even change, the geometric structure. We're now looking at a monochalcolgenide, germanium selenide, and that has a rectangular unit cell. So that's a bit different to what we have seen so far. And let's first look again just at the geometric interference pattern. And now comes the challenge. You have to remember the parallel lines that we looked at. Yeah? So we looked at the Moiré introduction at parallel lines being twisted. And something very similar happens here when we look at rectangular unit cells being placed on top of each other and then twisted against each other. Not sure why this only plays once, but anyways. You see, indeed, as you go to small twist angle, there is a very large Moiré super that is emerging, and it's one-dimensional. So the natural question that you can now ask, this worked, good, don't have to walk. Is this one-dimensionality only on the level of, let's say, geometric interference, or will it actually propagate down to the electronic properties of the system? All right, so let's look at this at more detail. So we have a top and a side view of germanium selenide. This is A and B. And then we make, a twisted bilayer of these monochalcolgenides. We go to a rather small twist angle of 6.61 degrees. This is the smallest twist angle that we're doing here, because here you need to worry about spin-orbit coupling, and then the simulations get even more complicated. But you see very interesting physics, even at these relatively large angles of 6.61 degree. All right, so again, we push this through the, maybe I should say, this is the top view of this Moiré stack. And again, what's really different is the local registry of stacking. So in this blue region, it's stacked like this. In the red region, it's stacked like this. And that just varies as you go in the Moiré unit cell. Yeah? So now we can push this through the electronic characterization, and we see a picture like this at 6 degrees. And you see, there's a flat band. It's a bit hard to see in this resolution, but we have a zoom in E. There's a flat band separating off this conduction band manifold up here. And as you go to smaller twist angle, this is actually getting flatter. Yeah, so here in E, I have a zoom of this. It's just this red box being zoomed into. And this is a nice flat band, extremely flat, yeah? Even at 6 degrees. But it also has another, very peculiar feature. If you look at the Brillouin zone, this is the mini Brillouin zone. If you go from gamma to X, this direction, yeah? So it's this direction, and you see that it's flat, but it's dispersing a little. Now, if you go along the direction X to S, this is this direction here, this is completely flat, entirely flat, yeah? Then from S to Y, this direction, a little bit of dispersion, Y to gamma, flat again. What that means is electrons can disperse along this direction. They cannot disperse along this direction. And that's one dimensionality. Yeah? This is quantified here in this panel F. This is the DFT characterization, and we try two different functionals. So if you remember the tutorial of the first day, we talked about advantages and disadvantages of using different functionals in the DFT characterization. Here we compare two and just wanted to show that they give similar results. Yeah? It's a bit hard to read, but this is a twin axis. We have yellow data that relates to the right axis, and that's the overall bandwidth. Yeah? And this is illustrating the fact that when you go to small twist angle, the bandwidth gets smaller and the bands become overall flat. The other thing that is plotted at the left, this red axis, that is the ratio of electrons having, making a perpendicular move to an in-chain move. Yeah? This is plotted here with this red data, and you see, although the overall bandwidth, which is yellow, goes down, it's good, the bandwidth decreases overall, also the ratio of perpendicular to in-chain hopping also goes down. So it becomes more and more one-dimensional as you approach the low twist angle region. And then if you look at the wave function absolute value squared, at the gamma point of these 4 different bands that we have, you see that they also nicely reflect this one-dimensional chain structure, yeah, that you would expect. But you also see that there is a pattern, big charge bubble, small charge bubble, big charge bubble, small charge bubble in this one-dimensional chain. So the low energy model that describes this dispersion relation correctly is at low twist angle, is a one-dimensional ionic model where you have just a nearest neighbor hopping and an alternating potential that gives rise to this alternating, alternating charge sequence here. And if you now do the same thing as before, you add some Hubbard type of interactions, this local, if you remember, the first talk of today, then what this model is actually realizing is the 1D ionic Hubbard model, which is a prototypical model of condensed matter physics, simply because it shows a variety of very interesting phases. So I brought these phases here in this table. So you have a band insulator at very small interactions. You can tune into band insulating regimes. That's maybe not too surprising. At very large interaction, you will stabilize a mod insulating state. Remember the talk that we had, again, the first talk of today. Then if you go into this one-dimensional system and you dope here, somewhere, and you add a bit of interactions, then you will actually stabilize a Luttinger liquid regime because it's a one-dimensional system. The Fermi liquid paradigm is unstable. As soon as you add interactions, it will actually be replaced by Luttinger liquid. And then there's a very fancy phase, the so-called bond-ordered wave state, which is characterized by a spontaneous dimerization of the bonds. So you get a spontaneous symmetry breaking in the hopping across the bonds. So you get spontaneously strong bond, weak bond, strong bond, weak bond. All right, so now we can take these parameters, and again, we can characterize with respect to chemical potential. This is again half filling here. So this is with respect to the flat bands, right? So this is here. And this is, twist angle in a sense, the ratio of potential versus kinetic energy scales. Yes? No, I'm taking monolayer, and then twisting. And this is the dispersion in the 2D plane. So we don't have a Z direction. Okay, so we take these two-dimensional systems, we put them on top of each other, we twist. We get dispersion only in one direction, in this two-dimensional plane, and not in the other. So you can really take two-dimensional systems, effectively engineer one-dimensional physics. And that's because of this slightly rectangular unit cell. Maybe I should have said this. I mean, this unit cell here is rectangular. Yeah, it looks almost like a square, but it's not. It's almost a square. All right, so all of these phases show up quite prominently, with exception of this exotic bond order wave state. There's probably no hope of finding this. It's such a tiny, tiny fraction of the phase diagram. Very, very difficult. All right, so if you have any questions about, larger liquids and so, yeah. Yeah. Yes. So this epsilon naught is kind of this, it must give you basically this gap here, right? Mm-hmm. Yes, yes. You can see from this panel E. So the bandwidth here, well, I guess if you take this as the bandwidth, the bands come here basically, yeah? So it's not insanely far away as you can, I mean, okay, here you can really say, but it's not that they are separated off by a huge margin. So it's a bit like in the transition metal dichalcogenides, right? Where mm-hmm. Absolutely, yeah. So just to, I mean, I know you understand perfectly, but just to repeat for everyone. So the question is, of course, exactly right. I mean, the separation of this band to the thing that is not shown somewhere up here defines an energy scale. If my interaction strength can bridge from this to this, I should worry about excursions into that other band, yeah? Which has not been modeled here, yeah, just to be very clear. We have some preliminary understanding that that should still be okay. I would be more worried actually about the long range direction part being dropped off. I should have said this also again. In this naive study, we just by hand killed the long range tail, and we have no idea whether that's catastrophic, like in just bilayer graphene, right? Yeah.
Question. Are these 1D bands stable? Don't you think that there will be Pearl's distortion and other 1D physics that would come into play here?
You mean with this order, when you, let's say you have twist angle variations or some other kind
right,
of disorder?
and we have created these one-dimensional bands. Mm-hmm. And if we have electrons in those bands, they are effectively one-dimensional systems. So will there be like standard charge density wave formation along the one dimension that, like Pearl's distortion, for example, instabilities?
Ah, piles. Uh-huh. Yes, so we haven't studied this. So you mean like a phononic? That's right. Yeah. So this is one dimension in the sense of, Moiré lattice. So now you would have to move a Moiré lattice as a whole, right, for the piles instability to be activated. This is already also, I mean, I guess that's a question when you tune, let's say here, right? This is already gapped, right? So we haven't studied this, to be honest. My feeling is just, but I can't, this is more a feeling. That's not so relevant, but it's a guess, yeah. The problem, maybe I should say, the problem with this here is that experimentalists are struggling with exfoliating this down to the monolayer. Yeah. So testing your hypothesis on an experimental level. So theory would be very hard. You have to characterize the phonemic instability on these large systems, kind of hard, but okay, we can try. But experimentally, you could also ask these questions. Here, this is more complicated. There is similar physics in tungsten ditelluride, I think, being reported by Leslie Shoup and others, where they basically see a very similar effect. Effectively, one-dimensional system being engineered by Moiré. And they talk about natural liquid instabilities and so on. It's basically this kind of idea, just transferred to this other material. Yeah? All right, good. So I will look only at one of the remaining stories. These are stories with experimentalists. And I will probably just give you a very brief outline of what we did for twisted tungsten selenide, and then concentrate on excitons, which I think might be more interesting to you guys. So in this work, which is all due to Lingnan Wei, Lei Wang, and my student Amon Fischer, they looked at this kind of system, twisted tungsten diselenide. And in this system, you have very strong spin-orbit coupling. And the low bands, the flat bands that you get are, as a consequence, spin valley locked. Yeah? So you have the flat band, and it's locked to spin species. And why I brought this is just to highlight that you can also play this game of reducing the kinetic energy scales to promote other competing energy scales with other things than Coulomb or electronic interactions. You could also ask, now that I have these very, very small kinetic energy scales, are my few Tesla magnetic fields in my lab all of a sudden big enough to get Zeeman effects that are strong enough to spin polarize? And the answer is yes. We have these flat bands, and now because they are so flat, we can actually split them by typical few Tesla fields. This is this little cartoon here. Yeah? And then what you can study is the competition. Now you have kind of frozen out the kinetic energy scales, and now you can ask, can I study the competition between magnetic energy scales gapping out the system and Mott energy scales mapping out the system, gapping out the system, sorry. And we did this here, and from this study, there are two scenarios that you could consider if you start from, let's say, a Mott insulator. This is, again, relating to the talk that we had as the first talk today. If you start from such a upper and lower Hubbard band picture that we have discussed, you can ask, how do I actually go from this kind of insulator to, let's say, a Zeeman insulator where you just have single particle physics, but you have just pushed the bands of up and down against each other, yeah? So that you are in this gapped regime here. And from just the measurements of the resistance, you can show that it's not this regime, which is proposed usually, where you have a very large U, you have well-formed upper and lower Hubbard bands, and then you basically only think you already have frozen out the charge degree of freedom, and you have, let's say, an antiferromagnetic state, and your small magnetic fields can just flip all the little spins up because you only have a very small exchange energy T squared divided by U. From this measurement, it seems like we're more in this kind of moderate U over T regime, where the gap will actually close due to band broadening effects as you turn on the interaction, and then open again. Yeah? This is what we can say from the experiment. We can model this. The simple Hartree-Fock model is enough for this to capture this effect. And what this buys us is the insight that apparently it's so that this twisted tungsten diselenide sample that we looked at is in this moderate U over T regime. All right. So in the last couple of minutes, I want to look at another system, and that's relating to the last talk of yesterday, where we want to look at excitonic physics. Yeah, so we're making quite a jump, and we're now asking, can I control material properties on the excitonic level? Yeah, so we're taking a heterobilayer, tungsten diselenide, tungsten disulfide. We're stacking it up. Now we do get a Moiré interference pattern, even without twist. They have slightly different lattice constants, and you can play this Moiré interference with anything. Yeah, if it's just a slight mismatch in lattice constants, also fine. So you get a large scale. This is, pictorially shown here, Moiré superlattice that is trapping your excitons. And the excitons that I want to talk about are these interlayer excitons. Yeah, these were also the subject yesterday, where you make the electron in a defined layer. This is the lower layer here, and the hole is in the defined upper layer. They're fixed. And that defines a permanent dipole moment, and that can make these excitons interact very, very strongly, yeah? And long-ranged. Very nice. So it seems like a cool platform to play around with. Yeah? So what Levi at Purdue did is they looked at such a sample. They excited with just a laser a bunch of excitons. And if you have few excitons, what you see is this yellow line here. Yeah? And they can time resolve, how the exciton cloud that they create spreads over time, and it just shows diffusive behavior. That's what you would expect. Yeah? So it just kind of diffuses out the exciton cloud that you have made. Now, when they increase the density of excitons by just pushing the system harder, more laser power, you go to this regime up here. So you again see, I create the exciton cloud, it expands a bit. Sorry, this is size of the cloud in a sense, and this is time. Yeah? And then it freezes. Yeah? It's like just a regime where it seems to stop expanding. And then there's something setting in where I lose basically excitons. This is up here. Okay? So that's very, very strange, right? So my proposal is I have dipolar excitons. They have a fixed dipole moment. They can't flip their moment. So they're certainly repulsive, strong repulsive interactions. I make a bunch of them and they freeze. It's very, if you just think about your classical understanding of physics, it's very strange. If you take a bunch of particles and give them a lot of repulsion, bunch them more and more of them together, they should just expand. Yeah? It's like a bomb. But they don't. And this is a consequence of the lattice. Yeah? And this has been reported, this effect. I'm going to explain this in more detail in a second. I just want to highlight that before, that this has been reported in the field of cold gases. Yeah? So there are these reports in these papers that repulsion can bind particles. Because these are cold gases, this was all done on site. We have, long-range interactions, dipole interactions. The basic effect is actually not so weird. If you create a bunch of excitons, you make many of them, they will fall into this underlying Moiré lattice. Yeah? And then you have lattice sites where they are doubly occupied, and you have lattice sites where you have only one exciton, just by the profile of your laser. Now, these doubly occupied sites, they will decay away rather quickly. Now, what you end up with after a rather fast relaxation of these doubly occupied lattice sites is such a Mott insulating state. Okay, I'll finish up in 1 minute. So you have such a state, and now you can ask, how easy is it actually for this state to move any of its particles? If you want to go from this, move this guy up here, you're going to pay a huge, price of energy U. You don't want to do that. You can also ask, can I move this particle from here over there? That seems to be okay. But the problem is you have to conserve energy, right? You have lots of neighbors. This is this cartoon here. You have lots of neighbors. If you now want to look at the potential energy that this guy has, it needs to fit in the bandwidth of this, periodic potential. You have to convert that potential energy to something. It can go away. I mean, up to, let's say, energy uncertainty. So if this guy has lots of neighbors, it just has too much energy to convert into kinetics. So it's bound, but by repulsion. And it's a consequence of the lattice plus quantum mechanics. All right, so then these other plots show that we can reproduce this effect with tensor network simulations, but I want to finish up and give just 2 words of outlook. So we saw this picture a lot in this workshop. I just want to highlight, and this was mentioned by others, that this picture is great, but it has to be taken with a bit of caution because you get lots of easy, in-plane or out-of-plane relaxation when you stack these things. So in this work here, we have shown that if you take graphene and you make 30 layers of graphene on something and you twist a bit, that relaxation can propagate through the full stack, 30 layers deep. Yeah? So when you engineer, when you're going out in this world and you're trying to engineer your 2D materials, keep that in mind. It's not like Lego. A defining feature of Lego is constant lattice constant. Yeah? Otherwise, your Lego bricks won't work. All right, the other 1 word of outlook is why I think this is very interesting also in the field of Floquet and cavity engineering is this quenching of kinetic energy scales. Yeah? So you have gotten rid of the kinetic energy scales, and in turn, you could hope that other energy scales that are usually very difficult to make strong, such as coupling to a cavity and such, actually play an outsized effect. Yeah? And this is just how I want to connect to these other pillars. And with that, I'm done. I would like to thank all of my collaborators and all of you for listening in.
Please ask questions. We already had questions, but if you have, please don't hesitate to ask them.
Yeah. So nice talk. Just one thing, when you were talking about the twisted bilayer HBN portion, showing the flat bands coming up. So how do I experimentally try to probe those flat bands? It's an insulator, right? So
yeah, this is this is what I tried to mention. This is an extremely rigid insulator. So the problem is how to, for example, if you wanted to transport, you want to have some charges there. Yeah? And that is, of course, with just regular gating, you can forget that. What you could try, and people are trying this at Columbia, is try to take a laser and photodope. Yeah? This you could try. Yeah? So just, you take a laser that bridges this energy and you punch some holes in here and populate it up here. And then you could probe it.
But what kind of flat band physics are we expecting from this kind of an insulator usually? Like Usually, like in twisted bilayer systems, the correlated insulator states, superconducting states, I mean, all other transport behavior in magnetotransport, etc. In optical spectroscopy, if you're trying to do something, what kind of flat band physics are we expecting from twisted bilayer HBA? That's my question.
Okay, in optics. So what I'm proposing is use the optics only for photodoping to get the charge to get the filling right. Then you can take another probe to, for example, try to see whether it's D-wave superconducting. I doubt it, but you can try. Yeah. I guess you're right. The first step of photodoping already tells you the presence from the absorption spectrum. You will see that you have these flat bands and that there's lots of joint density of states because the band is flat. So I think the existence of the flat band you would see even on the step of photodoping, but the consequence of the collective behavior, of course, you have to take some other probe to it.
What was the twist angle for the WSE2?
That is around 4 degrees, 3.89, I want to say, but yeah, the paper is, I think, not on archive. I can tell you the number, but it's around 4 degrees. Should be. I mean, it's a very good question because that really depends. I mean, that determines a lot of the physics. So when we say moderate U over T, a different twist angle, might be in the very strong U over T or whatever. We don't know. Yeah. We were just happy that these samples were actually clean enough to even do this thing, because as you know, TMDs are horrible to work with in this twisted. I mean, not for us theorists, but.
I have a question. Was that the twisted bilayer SBN that gave the triangular lattice Hubbard?
Yes.
Okay. So my question is, was that just a simulation of the Hubbard model? What is the advantage of looking at the model in the Moiré? Okay. Are there any other materials that show triangular lattice Hubbard model other than the Moiré structure?
Okay. So the question is also very good. So there are other material systems where you maybe have a 3D stack, but the effective in-plane physics is modeled by a triangle lattice. I think what is nice about the Moiré system is that you actually have this continuous degree. So you have a triangle lattice that is 1, but you can tune the kinetic energy scales. That's, I think, the nice thing about this. If you could actually dope it, that's here, of course, the issue. But there are, I mean, in a sense, there's of course other materials where it's proposed that a triangular Hubbard model is the right description of the low energy physics. Right, usually it's very hard to control. I mean, the kinetic energy scale is kind of controlled by chemistry usually, right? And here we can, the new feature of all of this Moiré in general, I would say, is this control knob of bandwidth plus potentially topology. Here, topology doesn't play a role, but. Right. Oh, there's a question in chat. Okay. Do we still have time, or should I answer this offline?
Okay, the online participants, if you want to ask a question, you can unmute yourself and ask.
Okay, so there's a chat. In the chat, there's a question about why the formation of Moiré patterns due to twisting introduces new properties. Okay, check. It can produce various types of defects. Yes, absolutely. At the edge of the twisted bilayer region, there might be misalignment or discontinuities that create boundary effects, defects, which can be the source of an additional strain in localized states. Absolutely. Is there any effective ways to reduce these defects? Other than I have no idea. I mean, yes, I agree with everything that was said. It's full of defects. It gets even worse when you go away from graphene, so the things that we have been talking about. Are there other, clever ways of reducing that? I guess that's a question to experimentalists. I don't really know. So if there's some experimentalist in the room that has very clever ideas besides the conventional ones, but now probably no one wants to. So sorry, I'm completely incompetent to answer this question, unfortunately.